Okay, this is literally like the third time I've tried to record this. I had technical issues. So, if you can believe that. All right, so this number 6 says that a train engine pulls out a station along a straight horizontal track with 5 identical freight cars, each of which weigh 90 kilonewtons. The train reaches a speed of 15 millimeters per second within 5 minutes. And it wants to know what the magnitude of force does it experience on the first and the last of the freight cars. So, and we're ignoring air resistance and friction. So if I were to draw a picture of this, sorry, I went up the stairs too, so I'm all out of breath. All right, this is our engine, and it doesn't say anything about the engine's mass. It just says the weight of each identical car. So there's going to be a tension, right here, and there's going to be a tension right here. And it wants to know what the magnitude of the force between the cars on the first and the last of the freight cars. Okay, so it's wanting these two values, essentially. All right, if we were going to do our sum of forces in the y direction, we just have, zero, or normal force minus weight is equal to 0. As far as our x components, we have tension, right? And they're going to equal mass times acceleration in the x direction. So as far as the first one, it is pulling all of these cars. Like, this is having to endure the tension of all of those freight cars. So do we have a mass for all of these freight cars? No, we have a weight. So if you go back to your equation where weight is equal to mass times gravity, we could rearrange that and say that mass is equal to weight divided by gravity. So we could plug that in for mass there. Okay? And how many of them are there? Well, there's 5 of them. So we could say 5 times weight times gravity. Okay, so we've got 5 times 90 kilonewtons divided by 9.8 meters per second squared. Times our acceleration, and we don't have that. So how can we find that? Well, it gives us that the train reaches 15 meters per second. So it's like the final velocity. So we're going to assume that the initial velocity is just 0. And then if you convert 5 minutes into seconds, you should get 300 seconds. So the acceleration is 0.05 meters per second squared. So 0.05 meters per second squared. So you end up with 2.3 kilonewtons. Okay, now I didn't convert the 90 kilonewtons back into newtons. You could have, and then your answer would have been given in newtons. So either way on that one, it was really fine both ways. And then the last one, so if we were going to solve the tension for this guy, it's the same equation. It's just, is it having to pull all 5 of these cars then? Well, no, it's having to pull just this one. So when we go to do it, it's just 90 kilonewtons, you don't multiply by the 5 then. And you should end up with 0.5 kilonewtons then, I believe. All right. So I just wanted to do another one that involved tension and, you know, to show too how if you don't have the mass, but you're given weight, but you need to plug in for mass, then you might have to, you know, substitute that weight equation in for mass. All right. Another one that I have made a typo or two on. So this says that a student is moving into a dorm, that's supposed to say dorm room, on the 3rd floor, and he decides to use a block and tackle arrangement to move a crate 105 kilograms from the ground up to his window. So if he's moving it from the ground up to his window, it is going in the upward direction, meaning that it does have acceleration in the y direction. And it says that the breaking strength of the rope is 550 newtons. And it wants to know what the minimum time required to haul the crate to the level window, which is 30 meters above the ground. So it's wanting us to find time. So if it wants you to find time, then there's a good possibility that you're going to have to use a kinematics equation, okay? Because we're in forces, and force is equal to mass times acceleration, so no time is in that equation. Okay, so let me draw a picture of this because the original question did have a picture of this. You guys will see how bad of an artist I am. Okay, so from this pulley, there's another pulley that is actually holding this suitcase or whatever they're trying to get up to the dorm room. And it's like going around like this, okay? So we've got this tension, and this tension is what is experiencing this mass that's hanging down right here. Okay, so if it's going up to the 3rd floor or whatever, then there is no acceleration in the x direction. So we just need to involve the sum of the forces in the y direction on this one. And both of these tensional forces right here are going upward. So you've got like tension 1 plus tension 2. And then of course you have the actual mass or weight. So minus mass times gravity. And you can set it equal to mass times acceleration in the y direction. Okay? So we've got to figure out how to get acceleration, because if we can get acceleration, then we can probably get time. Okay, so that means that we need to take this and move it over. Well, it tells us that the rope has 550 newtons of force. Okay, so that's this rope that we've got on both situations. So 550 newtons plus 550 newtons minus the mass times gravity divided by 105 kilograms. So you end up with an acceleration of 0.676 meters per second squared. And then it's wanting us to find time. It gives us 30 meters. So we gotta go back up to our kinematics equations and look which one actually gives a distance and an acceleration and has time in it. Well, that would have to be the first one. So if I go back down, then I'm gonna write this equation. Well, if it doesn't give an initial position, then we're going to assume that that's 0. Should have been on the ground, right? And the initial velocity doesn't give an initial velocity, so that's going to be 0. So if we plug in 0.676 for acceleration, and if we plug in 30 meters for that final position and solve for time, you should get that time is equal to 9.4 seconds. Okay? Obviously, on a question like this, I would have to give you an image. Okay? So now some of them I don't. Some of them you have to read the question, like with like this one, number 6, or even with number 5 with the suitcase. One like this though, number 7, I would have given you some sort of image to have looked at. Okay? Or at least a better describing question. All right, number 8, I kind of wrote on it a little bit. It says that a passenger weighing 598 newtons rides in an elevator. What is the apparent weight of the passenger in each of the following situations? In each case, the magnitude of the elevator's acceleration is 0.5 meters per second squared. And it says that the passenger is on the first floor and has pushed the button for the 15th floor, and the elevator is beginning to move up. This was the example that I wanted to do the other day on Monday, but I didn't have enough time, so I went ahead and put it on the review. Okay. So we've got this person that's weighing 598 newtons in an elevator. And, you know, it would be really cool to take a bathroom scale into an elevator and actually see this happening. But it wants to know basically what the normal force is on that person. So if you think about it, as the elevator is going upwards, what does your body tend to do? It kind of pushes downwards, right? So if you had a bathroom scale, like that you were standing on an elevator, if you were going upwards and it was accelerating, you should start to, well, it would appear that you were weighing more on the scale. So let's see how this works out. So you've got normal minus weight is equal to mass times acceleration in the y direction. Okay, so we're going to solve for the normal. We've got mass times acceleration plus weight. Okay, so did it give us a mass? No. But, again, we can find that by taking the weight that it gives us divided by 9.8. Remember this equation. So we have 598 newtons divided by 9.8 meters per second squared times the acceleration. So if it's going upward, if it's going upward and you are, you know, it doesn't say that it's slowing down or anything, it just says that it's beginning to move upward. So you have an acceleration that's positive. It's 0.5 meters per second squared plus the weight of the person. So if you do all of that, you should get a force of 629 newtons. Okay. Now, if the elevator is slowing down as it nears the 15th floor, then, and it says that the elevator's acceleration is 0.5 in all cases. So, but if it's slowing down, then that means that what happens to the acceleration as far as sign, that means that it would be negative. So as far as our equation is concerned, nothing changes. You still have this mass times acceleration plus the weight. The only thing that's different in this is that instead of it being positive 0.5, you end up with negative 0.5 meters per second squared. Still have to add the weight, and you should get 567. So, you know, right before you reach the 15th floor, you probably feel like you're kind of like going upwards a little bit. It would be similar to if you were going down in an elevator, you would feel as if you were sort of, your body was kind of going upwards a little bit. And if you had that bathroom scale in there with you and you were standing on it, your weight should look like it's actually getting smaller. Okay, so this is the apparent weight section of the chapter. All right, that is the end. Again, if you guys have any questions, let me know.